Hi, and welcome to the 37th day of Just Start Programming, the Rust programming language. Today is a Friday, so today we will start looking into the advanced features of Rust. So we will revisit advanced traits once again and then move on to advanced types. Let's try to see how much we can cover today. So join me once again live in one take, no shortcuts and no secrets. Let's just start programming. Right, so here we are. Let's backtrack a little bit. I think we were rushing yesterday to cover as much as we can for advanced traits, so now it's a good time to do a little bit of review. Advanced traits. Okay, so advanced traits. We first covered traits in chapter 10. That is several weeks ago, it seems, chapter 10. But we didn't discuss the more advanced details. Now that you know more about Rust, we can get into the nitty-gritty. Associated types. Associated types connect a type placeholder with a trait, such that the trait method definitions can use these placeholder types in their signatures. An implementer of a trait will specify the concrete type to be used instead of the placeholder type for the particular implementation. That way, we can define a trait that uses some types without needing to know exactly what those types are until the trait is implemented. We've described most of the advanced features in this chapter as being rarely needed, so special cases. Associated types are somewhere in the middle. They're used more rarely than features explained in the rest of the book, but more commonly than many of the other features discussed in this chapter. One example of a trait with an associated type is the iterator trait that the standard library provides. The associated type is named item and stands in for the type of the values the type implementing the iterator trait is iterating over. Okay, we read through that once again. One example of a trait with an associated type is the iterator trait that is a standard library provides. That the standard library provides. The associated type is named item and stands in for the type of the values the type implementing iterator trait is iterating over. So the type the iterator trait is iterating over is item. The definition of the iterator trait is as shown in 20-13. Trait iterator, you have item type. Then next, self item. Okay, the type item is a placeholder, and the next method's definition shows that it will return values of type option self item. Okay. Implementers of the iterator trait will specify the concrete type for item and next. So item is the placeholder. So the one who is implementing the iterator You specify the concrete type for item, and the next method will return an option. So the signature is next, it will return option containing the value of that concrete type for whatever it is. Associated types might seem like a similar concept to generics, in that the latter allows us to define a function without specifying what types it can handle. To examine the difference between two concepts, we look at an implementation of the iterator trait on a type named counter that specifies the item type is U32. Okay, so type item implements iterator for counter where the type item is U32. Okay, so you say type item here, and here type item is of type U32. And then the next function needs to be implemented from this iterator trait. So there's a code snippet here. This syntax seems comparable to that of generics. So why not just define the iterator trait with generics as shown in 20-14? So you can do generics as well, like this. Type T. Okay. Okay, what's the difference? The difference is that when using generics, as in 20-14, we must annotate the types in each implementation, because we can also implement iterator string or counter or any other type. We could have multiple implementations of iterator for counter. In other words, when a trait has a generic parameter, it can be implemented for a type multiple times, changing the concrete types of the generic type parameters each time. Okay, so you're changing the concrete types of the generic type parameters each time. When we use the next method on counter, we would have to provide type annotations to indicate which implementation of iterator we want to use. With associated types, we don't need to annotate types because we can't implement a trait on a type multiple times. Okay, so you cannot implement a trait on a type multiple times. In listing 20-13, with the definition that uses associated types, we can choose what the type of item will be only once. Oh, so this can be chosen only once, because there can be only one MPL iterator for counter. We don't have to specify that we want an iterator of U32 values everywhere that we call next on the counter. Okay. Associated types also become part of the trait's contract. Implementers of the trait must provide a type to stand in for the associated type placeholder. Okay, stand in. Associated types often have a name that describes how the type will be used. And documenting the associated type in the API documentation is a good practice. Okay, default generic type parameters and operator overloading. When we use generic type parameters, we can specify a default concrete type for the generic type. This eliminates the need for implementers of the trait to specify a concrete type if the default type works. You specify a default type when declaring a generic type with the placeholder type equals concrete type syntax. Okay, so this one becomes the default type. A great example of a situation where this technique is useful is with operator overloading, in which you customize the behavior of an operator, such as plus, in particular situations. Rust doesn't allow you to create your own operators or overload arbitrary operators, but you can overload the operations and corresponding traits listed in stdops by implementing the traits associated with the operator. For example, listing 20-15, we overload the plus operator to add 2-point instances together. Okay. We do this by implementing the add trait on a point struct. Okay, so let's see. You have point struct where you have x and y. So the objective is to add point instances together. And over here you have implements add from this stdops for point. And then the type, the placeholder, output equals point. And then since we are implementing the trait add, for sure it will have an add function signature where it takes self and other as point, and it will return point. So point x is self x plus other point x, y is self y plus other point y. Okay, so here then this is how it will look. Point x plus point. Okay, so that would be 1 plus 2, and then of course you have assert equals 3. Implementing the add trait to overload the plus operator for point instances. It's overloading the plus operator. Okay, so to overload, it says you need ops, and then add, implement add. So this part here is advanced traits, where you specify the type like this. Okay, the default generic type in this code is within the add trait. Here is its definition. So default will follow the syntax default generic type. So here you have RHS sub. What is RHS? Add RHS is, I think, right hand something, right hand side. Yeah, right hand side equals self type output. And then you have add self right hand side self output. So output and output is the type item, just like for iterator. So output is, in this case, is point. This syntax is called default type parameters. This one. Default type parameters. The RHS generic type parameter, short for right hand side, defines the type of the right hand side parameter in the add method. If we don't specify a concrete type for right hand side, we implement the add trait. The type of RHS will default to self, which will be the type we're implementing add on. Okay, so I'm just curious to see if we can do something like this where we add. I think there is a what was that? Builder pattern. Let me just Google it just to refresh my memory. I'm not sure if we have that in Rust, but at some point a long time ago came across with this builder pattern Java. Implement the builder pattern in Java. Let's see how we can relate this to Rust. Advantages of builder pattern, flexibility. Pattern allows us to create objects with varying configurations without cluttering our code base with multiple constructors or setters. Yes, I was not sure if that's what it meant, but let's skip to that and see how it looks like. Build method. Oh, it looks a bit different. But I was hoping you can just simply add, for example, here, in this case, it's a post. You just add a title, add a text category, build. So I'm sorry, it's a little bit different. I was just thinking if we can replace this with the plus operator, something similar. I'm not sure if that's possible. Yeah, but anyway, let's continue. Oh, may not be a very good example. Builder pattern may not be a very good example. Okay, anyway, please disregard that. Where were we? When we implemented add for point, we used the defaults for right hand side because we wanted to add 2-point instances. Okay, let's look at an example of implementing the add trait where we want to customize RHS type rather than using the default. We have two structs, millimeters and meters, holding values in different units. This thin wrapping of an existing type in other struct is known as the new type pattern, which we describe in more detail in the using the new type pattern to implement external traits on external types section. We want to add values in millimeters to values in meters and have the implementation of add do the conversion correctly. Okay, so two different structs. We can implement add for millimeters with meters as the right hand side. So millimeters left hand side and meters is the right hand side, as shown in 20-16. Okay, so we have struct millimeters, meters. Okay, so add meters for millimeters. Okay, so add placeholder default generic type would be meters, while here the output is millimeters. So add self other, which is in meters, the output would be millimeters. So millimeters self dot 0 plus other dot 0. Okay, self is the 0 is the first element, I suppose. Okay, the first element is times 1000. To add millimeters and meters, we specify IMPL add meters. To set the value of the right-hand side type parameter instead of using the default self. Okay, so meaning we are using meters as the right-hand side. You'll use default type parameters in two main ways. To extend a type without breaking existing code. To allow customization in specific cases most users won't need. The standard libraries add trait is an example of the second purpose. To allow customization in specific cases most users won't need. Okay. Usually you'll add two like types. Okay, so just like in the previous example, two like types, both point, struct. But the add trait provides the ability to customize beyond that. Using a default type parameter in the add trait definition means you don't have to specify the extra parameter most of the time. In other words, a bit of implementation boilerplate isn't needed, making it easier to use the trait. The first purpose is similar to the second, but in reverse. If you want to add a type parameter to an existing trait, you can give it a default to allow extension of the functionality of the trait without breaking the existing implementation code. Okay, so that's the reverse. So you provide a default to give it a you give it a default to allow extension of the functionality of the trait without breaking the existing. So default is the existing implementation. Okay, so that's how it is. I think this is another way. Disambiguating between methods with the same name. So methods with the same name. So add and add. Same name, function add. Okay, nothing in Rust prevents a trait from having a method with the same name as another trait's method. Nor does Rust prevent you from implementing both traits on one type. It's also possible to implement a method directly on the type with the same name as methods from traits. Okay. Implement a method directly on the type with the same name as methods from traits. When calling methods with the same name, you'll need to tell Rust which one you want to use. Yeah, because it might be ambiguous. Consider the code in 20-17, okay, 20-17, where we have defined two traits, pilot and wizard, that both have a method called fly. Okay, let's see, pilot, fly, wizard, fly. Okay. We then implement both traits on a type human. Okay, so you have struct human, implement pilot for human, implement wizard for human. So now you have in human you have both fly. Okay. We then implement both traits on a type human that already has a method named fly implemented on it. Each fly method does something different. Okay, so even human also has fly. Okay. When we call fly on the instance of human, the compiler defaults to calling the method that is directly implemented on the type. So I assume it would be waving arms furiously. Okay. Put of this. Can be printed out. Yeah, correct. So we're talking about human person.fly. Running this code will print waving arms furiously, showing that Rust called the fly method implemented on human directly. To call the fly methods from either the pilot trait or the wizard trait, we need to use more explicit syntax to specify which fly method we mean. Okay, so everything, okay, it's connected to human. Okay, but how do we specify for pilot? How do we specify for wizard? Okay, here, human, person, then pilot, fly. Okay, so pilot, fly, person. What was pilot fly here? Pilot fly. Okay, self. Reference to self. So reference to a person. Person. And wizard fly reference to a person. But here, if person.fly is called, so okay, so that's why fly is the, what's the term? Associated function. It's an associated function. Okay, specifying the trait name before the method name clarifies to Rust which implementation of fly we want to call. It will also write human fly person, which is equivalent to person fly. But this is a bit longer to write if we don't need to disambiguate. Okay. So in a trait, okay, so pilot is a trait. To call the function that implements the trait of human, okay, so you can do something like this. All right, so that's good to know. Because the fly method takes a self parameter, if we had two types that both implement one trait, Rust could figure out which implementation of a trait to be used based on the type of self. However, associated functions that are not methods don't have a self parameter. Associated functions that are not methods don't have a self parameter. So these are associated functions. Why does it say don't have no, associated functions that are not methods don't have a self parameter. Okay, so it's stating that associated functions which are not methods don't have a self parameter. When there are multiple types or traits that define non-method functions with the same function name, Rust doesn't always know which type you mean unless you use a fully qualified syntax. So I think fully qualified syntax makes it explicit. For example, in 20-20, we create a trait for an animal shelter. Okay, animal that wants to name all baby dogs Spot. baby dogs. Okay, baby name Spot. We make an animal trait with an associated non-method function baby name. Okay, associated non-method because there's no self parameter here. The animal trait is implemented for struct dog. Dog implement. Where's the animal trait? Ah, here. Animal trait for struct dog. Okay, for dog. On which we also provide an associated non-method function baby name. A non-associated non-method function baby name. Okay, here in this case it's puppy. So this baby name is actually this one because we're implementing the trait puppy. So how do we distinguish calling baby name from dog versus baby name from animal trait? Okay, here a baby dog is called a, okay, so in this case it's struct dog baby name. So I think this would be this. Let's make a guess. It should be Spot. Let's print it out. Yeah, a baby dog is called Spot. Okay, but how do we call this part instead? Oh, we implement the code for naming all our puppies to Spot in the baby name associated function that is defined on dog. The dog type also implements the trait animal. Yes, this part. Which describe characteristics that all animals have. Baby dogs are called puppies, and that is expressed in the implementation of the animal trait on dog. In the dog baby name function associated with the animal trait. In main, we call dog baby name function, which calls the associated function defined for dog directly. This code prints the following. Baby dog is called Spot. This output isn't what we wanted. We want to call the baby name function that is part of the animal trait that we implemented on dog. So the code prints a baby dog is called a puppy. So yeah, so according to this, the objective is actually this one. But I think our analysis is still correct. Yeah, because we're just simply tracing this baby name Spot. But how do we do this part? Okay, because animal baby name doesn't have a self parameter, and there could be other types that implement the animal trait. Rust can figure out which implementation animal baby name we want. We will get this compiler error. To disambiguate and tell Rust that we want to use the implementation of animal for dog as opposed to implementation of animal from some other type, we need to use fully qualified syntax. Okay, fully qualified syntax. How do we do it? Okay, so yes, okay, so this is the way to do it. Dog as animal. So you need to be explicit. Dog as animal. Baby dog is called a puppy. Oh, so there's actually something amazing about this Rust book. Because we don't have dog and animal here, but it was able to run and show this part. I'm not sure if this part here is scripted. could be a compiler that understands. It will make use of these things here. That's quite nice actually. It's quite convenient. Okay. We're providing Rust with a type annotation within the angle brackets like this, which indicates we want to call the baby name method from the animal trait as implemented on dog by saying that we want to treat the dog type as an animal. Dog as animal. For this function call, this code will now print what we want. Okay. In general, fully qualified syntax is defined as follows. So you have type as straight, then function, whatever parameter you have here, or argument. Okay. For associated functions that aren't methods, there would not be a receiver. So if it's not a method, so there won't be a receiver. There would only be a list of arguments. You could use a fully qualified syntax everywhere. Then you call functions or methods. However, you're allowed to omit any part of this syntax that Rust can figure out from other information in the program. You only need to use this more verbose syntax in cases where there are multiple implementations that use the same name and Rust needs help to identify which implementation you might. Okay. So you only need to do this to disambiguate. Okay, next. Using super traits. Okay, what are super traits? Sometimes you might write a trait definition that depend on another trait. For a type to implement the first trait, you want to require that type to also implement the second trait. You would do this so that your trait definition can make use of the associated items of the second trait. The trait your trait definition is relying on is called a super trait. Super trait of your trait. For example, let's say we want to make an outline print trait with an outline print method that would print given value formatted so that it's framed in asterisk. That is given a point struct that implements a standard library trait display to result in xy when we call outline print on a point instance that has 1 for x and 3 for y. It should print the following. Okay, in the implementation of the outline print method, we want to use the display traits functionality. Therefore, we need to specify that the outline print trait will only work for types that also implement display and provide the functionality that outline print needs. You can do that in the trait definition by specifying outline print display. This technique is similar to adding a trait bound to the trait. Okay, so here it shows an implementation of the outline print trait. We have here format, so the trait outline print, format display, function outline print to the self. Okay, output self to string, and then output len. Okay, so it determines the length of the string so that here You can print asterisk repeat based on the length plus 4. Okay, so here length is this one plus 1, 2, 3, 4. So that's why you have this. Then the second one, repeat length plus 2. Length plus 2. Oh, you have asterisk. So asterisk. Then this one is length plus 2. You put space. So this length plus prefix space and suffix space. And this one is the output. So output is the actual string. Okay, so on and so forth. Because we've specified that outline print requires the display trait, we can use the toString function that is automatically implemented for any type that implements this display. If we try to use toString without adding a colon and specifying display trait after the trait name, we get an error saying that no method name toString was found on the type itself. Current scope. Let's see what happens when we try to implement outline print on a type that doesn't implement display. Okay, so point outline print for point. So point doesn't implement display. In this case, yeah, it will be using the display. Okay, to fix this, we implement display on point. Implement FFT display for point. And satisfy the constraint that outline print requires. So we need formatter. Then implementing the outline print trait on point will compile successfully. And we can call outline print on a point instance to display it within outline asterisk. Outline print for point. Okay. The next one. Using the new type pattern to implement external traits on external types. New type pattern, what is this? Okay, in implementing a trait on type in chapter 10, we mentioned the orphan rule that states we're only allowed to implement a trait on a type if either the trait or the type or both are local to our grade. It's possible to get around this restriction using the new type pattern, which involves creating a new type in a tuple struct. We've covered tuple structs in using tuple structs without name fields to create different types in chapter 5. The tuple struct will have one field and be a thin wrapper around the type for which you want to implement a trait. Then the wrapper type is local to our crate, and we can implement the trait on the wrapper. New type is a term that originates from the Haskell programming language. There is no runtime performance penalty for this pattern. Okay, so there's no runtime performance penalty. And the wrapper type is elided at compile time. Is elided. Oh, it means omitted when speaking. Okay. So it's omitted at compile time. As an example, let's say we want to implement display on vect t, which the orphan rule prevents us from doing directly because a display trait and the vect t types are defined outside our trait. We can make a wrapper struct that holds instance of vect t, and then we can implement display on wrapper that uses the vect t value shown in 20-24. Okay, so you have wrapper vect string and format display for wrapper. So I think the key point here is you have a wrapper that holds an instance of vect t. Okay. The implementation of display uses sub-0 to access the inner vect t. Okay. Because wrapper is a tuple. Okay, so wrapper is a tuple. Struct and vect t is the item at index 0. The wrapper is a tuple, and then vector t is at index 0 in the tuple. Then we can use the functionality of the display trait on wrapper. The downside of using this technique is that wrapper is a new type. So it doesn't have the methods of the value it's holding. We would have to implement all the methods of vect t directly on wrapper. Vect t is not wrapper. Such that methods delegate to sub-0, which would to treat wrapper exactly like vect t. If we wanted the new type to have every method in the inner type, new type to have every method in the inner type, implementing the deref trait on the wrapper to return the inner type would be a solution. Okay, dereferencing wrapper, you get to get vect. Treating smart pointers like regular references with deref trait. Yeah, so this is a difficult topic as well. It's quite advanced. Let's see later on once we completed this course and we have done this, and probably we'll try other implementations in Rust and see how we can make use of these smart pointers. For sure we might come across this deref trait somewhere in other grades. Okay, so let's just focus on learning the fundamentals of Rust first. Anyway, once we dissect some advanced code, for sure we can come back to this as reference. In chapter 15, yeah, so that's in chapter 15. Okay, if we didn't want the wrapper type to have all the methods of the inner type, for example, to restrict wrapper type's behavior, we would have to implement just the methods we do want manually. Oh, it's a long way to go, I think. This new type pattern is also useful when traits are not involved. Let's switch focus and look at some advanced ways to interact with Rust type system. Okay, so let's move on to the next one. Types, advanced types. Did we cover this yesterday? No. Okay. Advanced types. The Rust type system has some features that we have so far mentioned but haven't discussed. Let's start by discussing New types in general, as we examine why new types are useful types. Then we'll move on to type aliases, a feature similar to new types, but with slightly different semantics. We'll also discuss the, okay, so this, I think this is the macro. Macros are still over here. Okay, let's see. Using the new type pattern for type safety and abstraction. This section assumes you've read the earlier section, using the new type pattern to implement external traits on external types. Ah, that's the previous one. Okay. The new type pattern is also useful for tasks beyond those we've discussed so far, including statically enforcing the values. Statically enforcing the values are never confused and indicating the units of a value. You saw an example of using new types to indicate units in 20-16. Recall that the millimeters and meter structs wrapped U32 values in a new type. If we wrote a function with a parameter of type millimeters, we wouldn't be able to compile a program that accidentally tried to call a function with a value of type meters or plain U32. You can also use the new type pattern to abstract away some implementation details of a type. The new type can expose a public API that is different from the API of the private inner type. New types can also hide internal implementation. So again, hide internal implementation. For example, you could provide a people type to wrap a hash map that stores a person's ID associated with their name. Code using people will only interact with the public API we provide, such as method to add a name string to the people collection. That code wouldn't need to know that we assign an I32 ID to names internally. The new type pattern is a lightweight way to achieve encapsulation to hide implementation details, which we discuss in encapsulation that hides implementation details. Okay, chapter 18. Is it there? Yeah, object-oriented programming. Creating type synonyms with type aliases. Rust provides the ability to declare a type alias to give an existing type another name. For this, we use the type keyword. For example, you can read the alias kilometers to I32 like so. Okay, so type kilometers, actually I32. Now the alias kilometers is synonym for I32, unlike the millimeters and meters types created in listing 20-16. Okay. Kilometers is not a separate new type. Values that have the type kilometers will be treated the same as values of type I32. Okay, because here you're defining the type, so kilometers is I32. So it's like y I32 equals 5. Okay, because kilometers and I32 are the same type, we can add the values. Okay, so here of both types, and we can pass kilometer values to functions that take I32 parameters. However, using this method, we don't get the type checking benefits that we get from new type pattern discussed earlier. In other words, if you mix up kilometers and I32 values somewhere, the compiler will not give us an error. The main use case for type synonyms is to reduce repetition. For example, we might have a lengthy type like, okay, so box, dynamic, function plus send. Writing this lengthy type in a function, signatures, and as type annotations all over the code can be tiresome and error prone. Imagine having a project full of code like that in listing 20-25. Yeah, so this is quite complex. Yeah, because here you see F becomes this one. We can avoid doing this by creating like a, what do you call this, an alias. Synonym or alias. Okay, let's continue. A type alias, yep. A type alias makes this code more manageable by reducing the repetition. We've introduced an alias named thunk for verbose type and can replace all the uses of the type within shorter alias thunk. So instead of putting this in, you can create a type alias like this and you just replace it with thunk. Okay, this code is much easier to read and write. Choosing a meaningful name for type alias can help communicate your intent as well. Thunk is a word for code to be evaluated at a later time, so it's an appropriate name for a closure that gets stored. Type aliases are also commonly used with the result type for reducing repetition. Consider the stdio module in standard library. I/O operations often return a result to handle situations when operations fail to work. This library has stdio error struct that represents all possible errors. Many of the functions in stdio will be returning result, where the E is standard for I/O error, such as these functions in the write trait. Okay, write trait, write. Okay, so it returns result error. So this one also result error, result error, result error. The result dot error is repeated a lot. As such, stdio has this type alias declaration. Oh, okay, because here you have view size, this one is empty. Type result T, standard result T, stdio error. Because this declaration is in the stdio module, we can use a fully qualified alias, stdio result T. That is a result TE, with E filled in as stdio error. The write trait function signatures end up looking like this. This one is result T. The type alias helps in two ways. It makes code easier to write and it gives us a consistent interface across all of stdio because it's an alias, just another result T, which means we can use any method that work on result T with it, as well as special syntax like the question mark operator. The never type that never returns. Okay, Rust has a special type named exclamation that's known in type theory lingo as empty page, empty type, empty page, empty type, because it has no values. We prefer to call it the never type because it stands in place of the return type when a function will never return. This code is read as function var returns never. Functions that return never are called diverging functions. We can create values of the type exclamation mark, so var can never possibly return. But what use is a type can never create values for? Okay. Recall the code in listing 2-5, part of the number guessing game. We've reproduced a bit of it here in 20-27. At the time we skip over some details in this code. Chapter 6, we discussed that match arms must all return the same type. For example, the following code doesn't work. Okay, and error. The type guess in this code would have to be an integer and a string. And Rust requires that guess have only one type. So what does continue return? How were we able to return a U32 from one arm and have another arm that ends up with continue? In listing 20-27. Underscore is anything else. Okay. For example, the following code doesn't work. Okay, underscore 5. The type of guess in this code would have to be an integer and string. So integer and string. And Rust requires that guess have only one type. So it should return only one type. So what does continue return? How were we allowed to return a U32 from one arm and have another arm that ends with continue? Okay, as you might have guessed, continue has a okay, so we call this never value. That is, when Rust computes the type of guess, it looks at both match arms, the former with the value of U32 and the latter with exclamation value. Because exclamation can never have a value, Rust decides the type of guess is U32. Okay, so meaning this one not possible. So it will use U32 instead. Error case, we never assign a value to guess. The never type is useful with panic macro as well. Recall the unwrap function that we call on option T values to produce a value or panic with this definition. Option T. Some and none. Okay, none we call panic. In this code, the same thing happens as in match in 20-27. Rust sees that val has the type T and panic has a type exclamation mark. So the result of the overall match expression is T. This code works because panic doesn't produce a value. It ends the program in the none case. Yeah, so it ends the program in the none case. We won't be returning a value from unwrap. So this code is valid. One final expression that has the type exclamation mark is a loop. Okay, so loop this will loop forever. Here's a loop that never ends, so exclamation is the value of the expression. However, this wouldn't be true if we include a break, because the loop would terminate when it got the break. Dynamically sized types and size traits. So Rust needs to know certain details about its type, such as how much space to allocate for a value of a particular type. This leaves one corner of its type system a little confusing at first, the concept of dynamically sized types, sometimes referred to as DSTs, dynamically sized types, or unsized types. These types let us write using values whose size we can only know at runtime. Let's dig into the details of a dynamically sized type called str, which we've been using throughout the book. That's right, not %str. But str on its own is a DST, or dynamically sized types. We can't know how long the string is until runtime, meaning we can't create a variable of type str, nor can we take an argument of type str. Consider the following code which does not work. S1 str, S2 str, how's it going? Okay, Rust needs to know how much memory to allocate for any value of a particular type, and all values of a type must use the same amount of memory. If Rust allowed us to write this code, these two str values would need to take up the same amount of space, but they have different lengths. $1 needs 12 bytes of S1, no, not the other S1. Needs 12 bytes of storage, and S2 needs 15. That's why it's not possible to create a variable holding a dynamically sized type. So what do we do? In this case, you already know the answer. We make the types of S1 and S2 a ampersand str rather than an str. Recall from string slices, chapter 4, that the slice data structure just stores the starting position and the length of the slice. Although the ampersand t is a single value that stores the memory address of where t is located, and ampersand str is two values, the address of the str and its own length. As such, we can know the size of ampersand str value at compile time. It's twice the length of a U size. That is, we always know the size of ampersand str, no matter how long the string it refers to is. What's that? That is, we always know the size of ampersand str, no matter how long the string it refers to is. In general, this is the way in which dynamically sized types are used in Rust. They have an extra bit of metadata that stores the size of the dynamic information. A golden rule for dynamically sized types is that we must always put values of dynamically sized types behind a pointer of some kind. So we can combine str with all kinds of pointers, for example, box str or rcstr. In fact, you've seen this before, but with different dynamically sized type traits. Every trait is dynamically sized type we can refer to by using the name of the trait. We mentioned that to use trait as trait objects, we must put them behind a pointer, such as a dynamic trait or box dynamic trait or reference count dynamic trait. To work with, what was DST again? Dynamically size types. Rust provides the size trait to determine whether or not a type size is known at compile time. This trait is automatically implemented for everything whose size is known at compile time. In addition, Rust implicitly adds a bound on size to every generic function. That is a generic function definition like this. Is actually treated as though we had written this. So t sized. Okay, by default, generic functions will work only on types that have a known size. Okay, generic functions will only work on types that have known size at compile time. However, you can use the following special syntax to relax this restriction. Oh, now there's a question mark. A trait bound on question mark size means T may or may not be sized. Okay, so T may or may not be sized. And this notation overrides the default that generic types must have a known size at compile time. The question mark trait syntax with this meaning is only available for size, not any other traits. Okay, so it's only meant for this. Also note that we switch the type of t parameter from t to %t. %t. Because the type may not be sized, we need to use it behind some kind of pointer. In this case, we've chosen a reference. Okay, next we talk about functions and closures. So we still have a little bit of time, so let's just continue and read about functions and closures. Okay, advanced functions and closures. This section explores some advanced features related to functions and closures, including function pointers and returning closures. Okay, what are function pointers? We've talked about how to pass closures to functions. You can also pass regular functions to functions. Okay, this technique is useful when you want to pass a function you've already defined rather than defining a new closure. What's that? When you want to pass a function you've already defined, okay, rather than defining a new closure. Function pointers sounds probably C++. Already forgot these things. Anyway, it's good to start again. Start again using Rust. Functions coerce to the type fn with lowercase f. Lowercase f. Not to be confused with fn closure trait. The fn type is called function pointer. Passing functions with function pointers will allow you to use functions as arguments to other functions. Okay, functions as arguments to other functions. The syntax for specifying that parameter is a function pointer is similar to that of closures as shown in listing 20-28, where we have defined a function at1 that adds 1 to its parameter. Okay, the function do twice Okay, do twice takes two parameters. Oh, okay, so do twice takes two parameters, a function pointer to any function that takes an I32 parameter and returns an I32 and one I32 value. The do twice function calls the function f twice, passing the argument value, and adds two function call results together. The main function calls do twice with arguments add1 and 5. Okay, so we have add1, then do twice. Okay, by having fn here, so it's a function pointer I32 which returns I32. Then you have another argument I32. Okay, so I think this is difficult to understand. Let's read from here. Okay, this code prints the answer 12. Why 12? Answer is 12. Okay, we specify that the parameter f in do twice is an fn or function pointer that takes one parameter of type I32 and returns an I32. Okay, so this is f. We can then call f in the body of do twice f. In main, we can pass the function name add1. Okay, add1. So we're passing it here because do twice can accept function reference. Okay. We can pass the function name add1 as the first argument to do twice. Okay, because of this. Then it takes another argument, which is 5, which is an I32. Okay, so it means 5 is called here using a function pointer. So imagine this is 5, then 5 plus 1 is 6. So this is 6 plus another one again, because you're doing it twice. Another one again. 5 plus 1 is 6. So 6 plus 6 is 12. Okay, so that's it. Understanding this is also quite complex. Okay. Unlike closures in Fn is a type rather than a trait, so we specify Fn as the parameter type directly rather than declaring a generic type parameter with one of the Fn traits as a trait bound. Okay. So function pointers implement all three of the closure traits, Fn, Fnmod, Fnmods. Meaning you can always pass a function pointer as an argument for a function that expects a closure. It's best to write functions using generic type and one of the closure traits, so your functions can accept either function or closure. That said, one example where you would want to only accept Fn and not closure is when interfacing with external code that doesn't have closures. C functions can accept functions as arguments, but C doesn't have closures, yeah. So I think that's the main purpose of having this. So it's mainly because of C functions. As an example of where you could use either closure defined inline or name function, let's look at a use of map methods provided by iterator trait, the standard library. To use map method to turn a vector of numbers into a vector of strings, we could use a closure. Okay, so map closure. And then I to string. Okay, so I is converted to string. Collect. Or we could name a function as an argument to map. So aside from closure, okay. Instead of closure, so here you can see this is how it would look like. Okay, so there is toString. We have toString, that is two twice. Name a function as the argument. Okay, function as the argument to string. Okay, but this one needs to return something. Note that we must use the fully qualified syntax that we talk about in advanced traits, because there are multiple functions available named toString. Yeah. Here we are using the toString function defined in toString trait, which the standard library has implemented for any type that implements display. Okay. Recall from enum values in chapter 6 that the name of each enum variant that we define also becomes an initializer function. We can use this initializer functions as function pointers that implement the closure traits, which means we can specify the initializer function as arguments for a method that take closures. Okay, so C listing 20-31 value stop, list of statuses, vector equals this one. Okay, using enum initializers with the map method to create status instance from here we create status value instances using each U32 in the range that map is called on by using initializer function of status. Some people prefer this style and some people prefer to use closures. They compile to the same code, so whichever style is clearer to you. Okay. Returning closures. Closures are represented by traits, which means you can't return closures directly. In most cases, where you might want to return a trait, you can instead use the concrete type that implements the trait as the return value of the function. However, you can't usually do that with closure because they don't have a concrete type that is returnable. Yeah. They don't have concrete type that is returnable. You're not allowed to use a function pointer as a return type if the closure captures any values from its code. For example, instead you would normally use the IMPL trait syntax we learned in chapter 10. It can return any function type using fn, fn1s, and fnmut. For example, the code in this thing 20-32 will work just fine. Okay, however, as we noted in closure type in inference and annotation, chapter 13, each closure is also its own distinct type. You need to work with multiple functions that have the same signature but different implementations. You will need to use trait object for them. Consider what happens if you write code like shown in 20-33. Okay, so it says here this one will not compile. It will not compile. Here we have two functions, return closure and returns initialized closure, which both implement fn i32. I32. Okay. Implement. This one is already looking complex. Return initialized closure. Okay, so it returns this. So this is the function part. Function returns I32. So eventually it will return I32. Okay. Notice that the closures that they return are different. Even though they implement the same type, if we try to compile this, Rust lets us know that it won't work. Okay, so we're near the end. Let's see. The error message tells us that whenever we return IMPL trait, Rust creates a unique opaque type. A type where we cannot see into the details of what Rust constructs for us. So even though these functions both return closures that implement the same trait, the opaque types Rust generates for each are distinct. This is similar to how Rust produces different concrete types or distinct async block even when they have the same output, as we saw in working with any number of features. Chapter 17. We have seen a solution to this problem a few times now. We can use trait object as in listing 20-34. Okay, so here box is used. Because then they will look the same. This code will compile just fine. For more about trait objects, refer to section using trait objects that allow for values of different types. Chapter 18. Next, let's look at macros. Okay. Macros is definitely interesting. It's something I also wanted to do. Okay, let's save that for another day. Let's end here for now and see you again tomorrow. Thank you so much.